Good afternoon, students. Welcome to yet another lecture of Advanced Green Manufacturing Systems course, and this is a course under the NPTEL MOOCs opportunity for you guys, and this course is offered jointly. It's offered from IIT Kanpur, and I am Dr. Deepa Philip from IME Department, IIT Kanpur, and we have been working on for a few days now on aspects of modeling, how to do optimization, and what are the major aspects that influence the greenness of a process and stuff like that. And we slowly moved into something called as design of experiments. How do we do experimental design, or how do we collect data, or what is the principle behind experimentation so that we can collect data and use that to optimize the performance of the system. So we have done some stuff on optimization, especially the modeling and using Excel to solve the optimization, and we have seen that aspects of it. And now we are back to the experimental aspects of it, or how the experimentation is being done, and how will that data collected through experimentation will allow you to set the particular value for a parameter or a factor so that the optimal output from the system is available. For the green manufacturing, our interest is to ensure that minimize the use of energy, minimize the wastage, minimize the usage of non-biodegradable cutting fluids, minimize noise, minimize health hazards, minimize ecological impacts, those kind of things. And also we would like to add a condition saying that without compromising too much on the productivity of the system. So then for that we will have to collect data, so only then we can optimize the behavior of the system. And this experimental design aspect that we are learning today is towards this focused more towards this data collection procedure, so that you can do optimization. So if you look into today's lecture on this advanced green manufacturing course or manufacturing system, today's lecture is titled Simple Comparative Experiments. Okay, and we are going to, our learning agenda is start with an example and then come up with the final the reasonably good set of guidelines for designing of these experiments. So let's start with an example today. Okay, what is going to happen, and this is like a simple example which might actually help you to understand the concepts of it. So a university or an institute is going to buy an automated pick and place soldering machine. So it's a soldering machine. What happens is like an electric machine, it takes a component, puts it there, and then solders by picks and place it, and then automatically solder it. And this machine is capable, this machine is capable of cleaning the printed circuit board using flux. So it first cleans the printed circuit board using flux. Printed circuit board is also known as PCB. Okay, this is used in electronic circuits. So it cleans the printed circuit board PCB using flux. Okay, and then it also preheats the board. Okay, so the board means printed circuit board. So this is the PCB board. Okay, and then what happens is it moves it. This is the PCB, moves it along molten solder. So solder is like a alloy of tin and lead and stuff like that. So it is available in a molten condition, and this PCB moves this along a molten solder. You can think of it in a bucket of it, and you can moving it along using a conveyor belt. So the system has a conveyor belt using which it actually drags this printed circuit board into the molten belt. Okay. By doing this, what happens? This solder will connect all the components placed on the board. So every components that are placed on the board. Okay. So this is basically connected using this solder. Okay. So this should be placed on the board. Okay. There are two options are available for these machines. One machine is capable of achieving 1% defective level. Okay. So that means whenever you are soldering, it results in only 1% of the solders being defective, and another is capable of giving you 5% defective level. So it will produce more number of defects. 5% defects is more number of defects in this regard. Okay. There is a major difference in the cost of the machines. Okay. Both these machines, the machine with the 1% defective level and the 5% defective level, both machines have major difference in the cost. Okay. And the issue is that when a defective board is produced, when the circuits are not properly soldered, then you require manual repair. So, a human being has to repair these circuit boards manually. That means you have to pay that person's salary, and more the number of defects, more time will be spent on repairing these boards, and hence it will be more expensive. Okay. And typical circuit boards designed by students contains 1500 soldering joints. So, in one way to think about it is, one machine, if you have 1500 solder joints, then implies 1% defective will be what? Will be 1 divided by 100 multiplied by 1500. Okay. So, this 1%. So, you can assume that there is 15 solder joints. So, per board, every board on an average you will miss 15 solder joints. When you talk about 5% defective boards, okay. So, what are we talking about? It is 5 divided by 100 multiplied by 1500. Okay. So, that is 15 times 5, that will be 75, right. 15 times 5 is 75, yes. So, you have 75 of these ones will be defective. So, this case you will repair, or you are manually repair, okay, 15 of these connections. Here you would require manually repair 75 of these connections. Okay. So, this is obviously, you can probably say that this machine gives you more defects, okay, more defects, but cost is low. This machine gives you very low cost compared to this is less defects, cost is high. Okay. So, the question is, which machine should be selected, which one should we buy, or which one should the university be buying this. So, this is a very simple example which allows us to consider or look into what we call as the experimental design aspects. Okay. So, the first thing that we need to think about is the, as I told earlier in the optimization also, we need to think about the variables. Okay. And here we are going to focus on the controllable variables. If you remember, we had drawn the diagram like this, the process or the system, we had the input, okay, and we had the output or response, okay, and we had multiple variables x i's. These are the controllable variables, and we had the zj's, uncontrollable variables, right. So, we saw the experimental design process in this. So, in this case what we are going to first talk about is what are the controllable variables. Major options of controllable variables, major options available for control variables are, what are those major options for us? One option is could be solder temperature, okay. Solder temperature is the molten solder, okay, how hot it is, okay. So, we are more interested in the temperature of it, which gives you the molten solder. So, I told you in the example that, and moves it along the molten solder. So, this statement. So, the molten solder, what is the temperature of the molten solder is what we are talking about here. Another example is, another possible option is preheat temperature, okay. So, when we talk about preheat temperature, what we are talking about is the machine is capable of cleaning the printed circuit board using flux, then preheat the board, okay. So, what is that preheat temperature? That is something that we are interested in. It could be one of the options. Another option is the conveyor speed. So where did I get the conveyor speed? The conveyor speed I got it as, it basically says, and moves it along the molten solder using a conveyor belt. So it is moved along the molten solder. So the conveyor belt moves it along. So the speed at which this printed circuit board moves along the molten solder bath is an important thing. So what is the speed at which it is going? It can be millimeter per minute, centimeter per minute, or meter per minute, or something like this. Could be some speed. We don't know what the speed is, okay, and depending upon the speed, it could depending upon how it actually works. And we talk about another one as the flux type. Okay, what is a flux? Okay, the question is, what is the flux that is used? So where did this flux come from? Okay, so the flux actually came from, it says, cleaning the printed circuit board using flux. So whichever flux that you use might influence a cleaning process, and if it influences a cleaning process, then it might also influence the soldering. So you might want to look into what might be the fluxer, the flux type. Okay, the other one is the solder bath depth. Okay. So, or you can think about it as, what we are talking about here is, it is basically moves it along the molten solder. So, if you think about the system, it would probably be like you have a printed circuit board coming here, okay, in which there are many components that are installed on this. Okay, it's a resistor, transistor, that's a capacitor with legs and other things on it, and then it gets into a molten solder. This is like, let's say, your molten solder. So you might be interested in the depth of this, okay, how much the molten solder would be, or it can also called a solder bath depth. Okay, and this is your solder bath, and this gets dragged along this one. Okay, so that's another option, right? Then another possibility option is the conveyor angle. Okay, depending upon what angle. Okay, what angle does the PCB gets dragged in the solder bath. Okay, so that is one option that we have. Then we can also think about something called as the specific gravity of the flux. Okay, so you are anyway using flux for cleaning the board. So what is the specific gravity of the flux? That's one other aspect, and so on. There are so many aspects that you can do. Okay, I just listed some of it, and the question is, where did I get all these things? Okay, usually obtained from the problem statement and also by consulting others, okay, including experts. So you might want to go talk to a few experts who work in this area and figure out what is going on, and from there you can find out certain variables, and these variables we think we can control because, okay, some control option is available. Okay, this includes this also, right? So we can somehow control these variables. There is some conveyor speed, there could be a dial which you can twist, and then that reduces the control speed. Okay, all right. The next option that we have talked about, we are still in the variables. It is the uncontrollable variables. Okay, uncontrollable variables is you don't have any control over these guys, and there could be many, and some examples are, there are some examples, and the one example is thickness of the printed circuit board, or what we call as the PCB. Okay. Why you obviously would think that why this is a uncontrollable variable, why is this not a controllable variable? Because it is uncontrollable because usually bought from different vendors, hence different size, hence different thickness. So, since you mostly buy these PCBs from different vendors, you will probably get them in different thickness, and depending upon the thickness, it might impact the soldering of the or the amount of solder that is required, right? And various another one could be various components used on the board. Okay. And so it is like components will be, you can think about as resistors, capacitors, inductors, transistors, etc. Okay. You cannot control them because the reason is that these ones, depending upon, they all depend on the circuit design. Okay. How do you design the circuit? The design of the circuit determines what are the various components that you are going to use in this, right? The other one is circuit layout on the PCB. Okay. How is the circuit laid out? How no, this depends on the type of circuit. Okay. Varies from application to application. So, what we are saying here is that in this PCB system, the circuit layout can also be a factor, but the point is you cannot control it because it is depending upon what the type of the circuit it is and what application it is being used for. So, you have no control over it, you cannot control it, the circuit board comes to you as designed by somebody else. Okay. Then there is something called operator of the machine. It's very hard to control operators. Okay. Most times human operators are uncontrollable. You cannot control human operators most of the time, purely because of the fact that they have their own mind and human operators do things in their own fashion. So, you cannot really do much about it, right. Then we talk about another example of this will be humidity in the laboratory. If the factory has too much of a humidity, then it's like depends on weather, Okay. So, whatever the weather is, the humidity is influenced by that, you cannot control the weather. So, it's like something that is given to you and you have to work within that particular humidity. Okay. So, all these factors, okay, can be measured, can be quantified, but no option to control. You cannot control these factors at this point. Okay. So, because they are available, they are there, you can measure it, you can quantify it, but you can't control it. Okay. Then we talk about the last variable, which is called as the response variable. Okay. So, the response variable is the output, or for that matter, in the previous diagram, if you think about it, we are talking about response variable as this. Okay. So, how do you decide the response variable? Okay. So, one of the things that is the usual question that we ask is what is the, in this case it is what is the particular department interested in measuring. Are they interested in measuring how many defects are there on the circuit board, or are they interested in measuring the cost of the system? So that is one question that they are, that is usually tells you what is the response variable. Okay, is cost effectiveness a top priority? Is cost a major priority here? Okay, or is quality more important? Okay, how the cost versus quality will be compared. Okay, the question here is we are going to compare, how are we going to compare the cost versus quality, right? Uh, one aspect of it is 1% defect on 1500 solder joints will result in major manual touch up, manual corrections. So, if you get 1% defective on 1500 solder joints, you will have to have major manual intervention to solve it. Okay. So, then the next part is 5% defects will be lot more. Okay. There will be lot more manual touch up that you will require in this case. Okay. So, the other thing you can think about is, does the price difference of both machines, both pick and place soldering machine justify the increased operating expenses, Okay. And where is the operating expenses coming from? Manual interventions or manual repair or repair of the solder. Is the manual, by paying that much money more to an individual, is this justified? Is this increasing operating expenses justify the price difference between both these machines, right? Okay. So, there are many questions that you can come up with, and from there you can decide what is going to be, okay, what is going to be the response variable. One way to think about it is, you can think about as maybe better to identify which factors, okay, controllable and uncontrollable together, okay, affects the occurrence of defects during soldering. So, what we are saying here is, maybe instead of looking into all these kind of things, all these aspects, it may be better for us to identify which are the factors, both controllable and uncontrollable together, affects the occurrence of defects in soldering, or the defects in soldering, what are the causes of that, what are the factors that are causing the. So, what are the factors majorly influencing the soldering defects? Okay. So, one way to think about is, if we can somehow control the defects on soldering, okay, if this 1%, 5% defects, okay, if this can be reduced, can it be reduced? okay, or what is causing these defects. If we can understand that and try to solve that problem from that side, then the problem of which machine to buy would probably be this could be a better problem that we can state in that way. Okay. So, the response variable is always dependent upon what is the criteria or what is the aim of the experiment that or what you are actually trying to do. But remember, the response variable is not set in concrete. You might start with a response variable, as the time progresses you realize that is not the right thing to do, and then you typically go back and change. That is why experimentation is an iterative process, or it is a process that you repeat frequently. So, let us go back to the basic principles of experimental design, and now what we are going to do is we are going to go through what are the major guidelines of designing an experiment and how are we going to achieve that. Okay. So, the first thing that you need to understand the term is the statistical design of experiments. Statistical design of experiments. Okay. So, this term, what is this statistical design of experiments? Okay. It is the process, okay, process of planning the experiment. It is a process of planning the experiment, so that proper data can be collected, so So, it is first the planning of the experiment, so that proper data can be collected, that is analyzable by statistical methods, by various statistical methods, okay, resulting in valid and objective conclusions. So, the statistical design of experiments, it is the process of planning the experiment. Okay. So, you are planning the experiment, so that, why do you need to plan the experiment? So that proper data can be collected. The main aim is to collect data in the proper data. Okay. That is analyzable. So, the reason of is you collect the data that is analyzable by various statistical methods, right. And once you have proper data that can be analyzed by different statistical method, you can draw valid and objective conclusions. So, remember here this phrase, okay, garbage in, garbage out. So, if you do not collect data, if you do not collect proper data, okay, no proper data, if you do not have proper data, then you will get garbage out of the system. Okay. So, you plan the experiment, you have to plan the experiment, so that proper data is collected, that is analyzable by various statistical method, so that you can draw valid and objective conclusions from the data. Okay. Mandatory if the aim is to draw valid conclusions from the data. Okay. If you are just doing an experiment for the sake of experiment, then probably statistical experimental design is not a big deal. But if you want to draw valid conclusions from the data, if that is the aim for you have, then statistical design of experiments is a mandatory thing. Okay. And there are two aspects, okay, to any experimental design, to any experimental problem. Okay. There are two aspects to any experimental problem. Number one, okay, design of the experiment. Okay. And number two is the statistical analysis of the data. analysis of the data. Okay. So, the design of the experiment is, what you do is, it is ensure that no garbage data. So, this design of experiment or experimental design or design of experiment ensures that you are not collecting any garbage data. And statistical analysis of data, it allows for valid and objective conclusions. Okay. So, you cannot draw valid and objective conclusions if you do not have proper data. So, these two steps are interrelated. So, you can say that the steps 1 and 2 are interrelated. Okay. You cannot have one if you do not have the other. Okay. So, if you do have garbage data, then you cannot draw valid and objective conclusions. If you do not have a proper statistical analysis, if the data is not collected in the format that you can apply statistics, then you can't draw conclusion. So, what data you collect and which format you are going to analyze it is quite important in this case. Okay. So, now we get into what we call as guidelines for designing experiments. Okay. How are we going to design experiments, right? So, the step 1, the first step in this regard is identify problem statement. Okay. So, people say this is the first thing you need to do. Okay. Identify the problem statement. Very obvious statement. It appears to be an obvious statement. Okay. But often is not simple. Okay. So, when somebody says identify the problem statement, it looks like it is obvious, it is very simple, but often it is not, it is usually not a simple thing to do. Okay. Usually requires soliciting of information or soliciting or obtaining input. Okay. Usually requires soliciting or obtaining input from all concerned parties. All concerned parties. The better term for this is stakeholders. Okay. This includes customers, engineers, okay, operators, finance people, sales persons, etc. So, you have to take input from as much as possible, wherever you can get inputs from all concerned parties, okay, or all stakeholders you have to collect input. So, before you identify the problem statement, you have to solicit or you have to obtain input from all your stakeholders. Okay. So, this implies what? Okay. Hence, a team approach is recommended for designing experiments. Since you have to have all this information solicited from different places, okay, is recommended. Okay, recommended for. Okay. So, it is usually recommended that a team approach is followed, where you create large multidiscipline teams and you solicit information from those teams. Okay. So, that is the first part. It appears to be an obvious statement, but it is not an obvious statement. Then comes the second aspect, second part of this one. Okay. So, that is, we call it as choice of factors, levels and range. range. Okay. So, what we are doing here is when potential factors, when factors that can potentially influence the system performance, when you are considering those factors that can potentially influence the system performance, okay, can be both controllable and uncontrollable factors. Okay. When factors that can be potentially influence the system performance, okay, then okay, when you are looking into these factors, when the factors that can potentially influence, you think that it can influence the performance of the system, can be both controllable and uncontrollable factors, both levels and range are required for limiting experiment data collection. Okay. So, for example, if you say in the previous case one of the controllable factors was solder temperature, right. If I take the temperature range as 0 to infinity, then bad range, okay, because you want to limit it to something so that you can actually control that value and you can collect appropriate data to do the analysis, right. And mostly controllable factors, they are divided into two, number 1, number 2. Okay. The first one is called as design factors, okay, and the number 2, the second one is called as held constant factors. Okay. So, the major two divisions are design factors and held constant factors. So, the design factors are, they are selected for study, okay, you use them for study, and the held constant factors are can exert some influence in the output, okay, or response. It can do some influence on the output or the response, okay, but usually held constant during experiment. Why are you keeping it constant? Because the impact on the response, the impact on the output is usually much low. Hence, you really do not want to vary them during the study. So, you keep them as constant values. There is a third thing that you can think about, okay. It is also there, which is called as allowed to vary factors, allowed to vary factors. Okay. So, these are the selected for study and they are strictly controlled. Okay. You basically strictly controlled or changed. The values are strictly controlled and changed in this regard. In this case, they are held constant, the held constant factors, because they exert very minimal influence on the output or the response and they are kept constant. The third cases, okay, they are similar to held constant, similar to 2, okay, held constant, okay, minimal impact, it does not have much impact on the output or the response. The major difference between this is, the major example of this is materials. Okay. You cannot control the materials that much. I mean, you say I am going to make bronze and I am going to use it, but if it is an alloy, then the composition of the alloy can vary from place to place. So, you cannot really control it, you cannot hold it constant. So, the difference between 2 and 3, okay, 3 is very difficult to keep constant. Okay. So, though most of the people consider as 1 and 2 design factors and held constant factors as the most important thing, there are certain factors, a small, very small set of factors, they have very minimal impact on the output, okay, very minimal impact on response, but you cannot really control them or you cannot keep them constant, hence you allow them to vary. Okay. So, that is the classic example of this is the materials aspect of it, right. So, we have gone through two of the major guidelines of the designing of experiments. Now, let us look at the further set of guidelines in this regard. So, the third one basically we say is selection of response variable. Selection of response variable. Okay. So, how are we going to select the response variable? Okay. We have to say we should be certain that the chosen variable, okay, we should be very particular, or we should be certain that the chosen variable provides useful information, information about the process. So, the first check in this case is we should be certain that it provides useful information about the process. The information that is about the process should be useful, so that you can make conclusions out of it, right. Okay. Usually there are multiple candidates for y. Okay. Remember, y is we use y to denote the response variables. Okay. Then how do we select them? Selected using a pilot study. Okay. We do a pilot analysis or a pilot run of the experiment, and the pilot study is typically used to decide which is the better one, okay, which is the better candidate that provides the most useful variables in this regard, response variable. Then the fourth one, okay, choice of experimental design. Okay. Now we are ready to collect the data, okay, and since we are ready to collect data, we have to involves considerations like, there are certain considerations that you have to do in this case. The first consideration is sample size, okay, which is how many data to be collected, okay, or this translates to what we call as replications, okay, how much of data that you need to collect in this regard. Okay. Second one is the suitable run order for experiment trials. Okay. We have to decide in which order you are going to collect the data. This is called as, in a way it translates to what we call as randomization. Okay. And then last one is determination of blocks, or what we call as blocking. Okay. Remember, we told in the previous presentation, replication, randomization and blocking are the three fundamental aspects of experimental design, and same thing comes here, or decide in the form of sample size, the run order, and what are the blocks. Okay. The reason is that these will result in analyzable data. Okay. We can have the data that can be analyzed out of this. Okay. That is the major reason why we do it this fashion. Now, the fifth one, okay, conducting or performing the experiment or performing the experiment. We are conducting or performing the experiment. Okay. Where we do is that ensure that process is monitored carefully to ensure that everything is done as per the plan. Okay. And where is the plan? Plan is this. Okay. So, when you choose the experimental design, you plan this. So, here is this one is plan everything. Okay. And do as planned. That is what happens in this case. All right. So, once this is done, what we do is we get into the third set of guidelines for the experimental design. This is kind of the last set of guidelines and the two more of them. Sixth one, okay. What we do is statistical analysis of data. Statistical analysis of data. Okay. So, where we are doing is ensure that results and conclusions are objective instead of judgmental. Okay. Instead of judgmental in nature. Okay. So, what you have to do is the statistical analysis allows that the results and conclusions are objective instead of the subjective or the judgmental in nature. Okay. Should help in developing the empirical model. Remember, we said this empirical model is required for us to optimize things or okay, work on it. Okay. So, what is the empirical model? An equation derived from the data, derived from the experimental data. Okay. You are deriving this equation from the experimental data that expresses the relationship between response, okay, that is y, okay, and important design factors. Okay. These are your x's. Okay. So, what you do is you develop an equation, you develop the empirical model, which is an equation that connects the experimental data. This equation is coming from the experimental data, and what it does is it expresses the relationship between y and the important design factors. So, as I said, y, here you get y as some combination of x of x's. Okay. So, that is what we are more interested in doing here in this part of this one. Okay. And then is the last part, the seventh step, right, is conclusions and recommendations. Conclusions and recommendations. Okay. Now, you think that is very easy to do, not necessarily. The conclusions and recommendations, the important thing for us is must draw practical conclusions. Practical conclusions, not just any conclusion. The qualifier word is we must be able to draw practical conclusions about results. So, practical conclusions about the result should be drawn and recommend appropriate course of action. Okay. We should recommend not just draw conclusion, we should also recommend a course of action, right. So you should be told, okay, this is the, in a way you can say it is the managerial implication. Okay. The managerial implication is cannot manage what cannot be measured. So, if you cannot measure it, you cannot manage it. That is the fundamental idea behind this. So, we are trying to ensure that we measure it. So, and so that we know what is the course of action, right. Then finally also is that you can say that follow up runs and confirmation testing should be conducted to validate conclusions. Okay. So, we should follow up the runs and we should do confirmation testing. Once we did the analysis and we say, oh, we are done, we got this y equal to some combination of x's, we built our model, but we should follow it up with follow up runs and confirmation testing to ensure that our conclusions are valid. Okay. Our conclusions are valid and practical, and the recommended course of action is correct in this regard. Okay. So, summarizing this, we have reached the end of our presentation, but summarizing this, what we are saying is that we found out why we do experimentation and why the experimentation, the planning to collect the data in the proper format, so that you can use statistical tools to analyze this data. Why is it important, and so what is the necessity of drawing valid and practical conclusions, and recommending a due course of action is important thing for us. And in this case, the due course of action is how to convert an existing manufacturing facility into a green manufacturing facility, or how do you design a green manufacturing facility as a fresh one. Okay. With this, we conclude today's presentation, and I expect you guys to read through this, follow it up, and keep practicing the experimental design aspects of this course. Thank you very much.